Hey folks, and welcome to Chapter 9, Acids and Bases. So Section 1, Part 1 today is all about acids and bases. And first, concepts in context. So here's a example from your textbook, and it has to do with metabolic acidosis. So obviously it says the word acid in it, and so this has something to do with acids and bases, and blood pH has something to do with acidity. So here's the situation. A marathon runner stumbles into an aid station, breathing heavily, acting confused. I don't know if anyone's ever done a marathon, but it's quite taxing on your body. Breathing heavily, not unusual. Acting confused, maybe is a little bit. So the nurse at the aid station measures the arterial blood pH, finds that it is below normal. As we will find out, below normal pH means more acidic. So low pH is high acidity. We'll get to that eventually. But the treatment given to this runner is to give an IV of saline plus an oral sodium bicarbonate. And the result is the runner recovers fairly quickly. Right? So the sodium bicarbonate somehow brought the pH back up to a normal range. And that is kind of motivating the rest of this section. We're going to come back to this exact same, the actual equation at the end. So here's a brief look at normal blood pH, right? When it says it's below normal. So it is very important to maintain blood pH. There's a regulatory system within your body that keeps things within this normal window right here. The proper organ function requires blood pH to be between 7.35 and 7.45. Okay, and this is maintained and regulated through acid-base homeostasis. So homeostasis is like a regulatory system in your body that keeps pH where it's supposed to be. And this has to do with sodium bicarbonate is a part of that. Acidosis is defined as pH less than the expected range, so less than 7.35, and alkalosis is a pH greater than 7.45 out of the range. And there's a little bit of a range where alkalosis is problematic but recoverable. But if pH gets above 7.8, right, then it says death. So same with acidosis. It's got about 0.6 or so, 0.4 range. And if it gets below that, it again leads to death. So pretty serious consequences, obviously, outside a fairly small window of blood pH. So it's really important to maintain this consistent homeostasis. So here's a look at how this can happen: cellular metabolism and metabolic acidosis. So metabolic is the mechanism through which acidosis can occur, and this is showing some equilibrium reactions across the top. Okay, and H plus right here is when we talk about measuring acid, it's actually measuring the H plus. And so CO2 can be taken up in the muscle cell, or oxygen can be taken up and it can release CO2, and there's a cycle here. But notice that if CO2 gets into the blood, think about your knowledge of equilibria, right? What happens to the equilibrium when CO2 concentration increases? It's going to shift the equilibrium this way to produce more carbonic acid, which will then shift the equilibrium this way to produce more H plus. And now we have a problem. If there's more H plus, there's more acidic. We just produced acidosis. So if CO2 cannot be flushed out of the blood, then this can happen. You can lead to acidosis. So the cellular metabolism produces substances that affect blood pH, such as CO2, as we just saw, and H plus ions. So the pH is maintained. You can think about like how do you get rid of CO2 in the blood? Well, you have to breathe it out. You have to exhale, right? So if you increase respiration to exhale more CO2, then that can keep blood pH maintained, or shifting the buffer equilibria to consume more H plus. So doing something else, for example, adding. Let's look at adding sodium bicarbonate. This right here is bicarbonate. So remember our runner who came in with a low pH, means high H plus concentration, and the nurse gave the runner some sodium bicarbonate, which would what? Shift the equilibrium back this way and back this way. So consume H plus, thus increasing the pH. So this is kind of cool stuff that we can do and that really matter in terms of healthcare and nursing. All right, so that was all kind of introductory to the first section, which is just acids and bases. And here's some examples of natural things that are acidic and basic. So oranges, citrusy things tend to be a little acidic, and chocolate and cacao is basic a little bit. Some other common examples is an antacid, right? So if you have heartburn, you can take medicine against that, and some of these contain milk of magnesia. That's like the name that people know, right? It's actually just a chemical name, magnesium hydroxide, which is MgOH2, and it's a base, right? So it's like kind of the opposite of an acid. That's why if you take it, it's an antacid, it's against acid. It can help to neutralize acidity. Yeah, so it's just an example. When you see an antacid, it's really a base that neutralizes. Okay, so what are acids and bases? Well, here's the chemistry definition. This is the Bronsted-Lowry theory. Your textbook also has the Arrhenius theory, which is slightly different definitions, but we're going to skip to the Bronsted-Lowry and not confuse ourselves. So in our definition, an acid is anything that donates H plus ions. Right? It produces them or gives them away, loses H plus ions. And then because we know that everything has to be balanced out, something has to take those H plus ions, and so that would be a base. Anything that accepts H plus. Okay, what does all this even mean? Now, I have a question for you to think about. What are the subatomic particles in a hydrogen atom? Right, so if you think back to chapter 2 and atoms and stuff, hydrogen, right? The first element, it has what? 1 proton and 1 electron. So with that, what would be the subatomic particles in a hydrogen ion, H plus? Well, all that's happened here, right, would be that it's lost an electron. So H plus is simply a proton, right? So when we say like acids and bases donate and accept H plus ions, well, we often also simply just say it's a proton. So an acid is a proton donor, or an H plus, right, ion, and a base is a proton acceptor. So that's the definition you need to know. we will give lots of examples now about these and ways to think about how they interact with each other, what it looks like in a reaction, and so on. Okay, but an acid, proton donor, base, proton acceptor. And I'm going to keep that definition up here at the top for the next mini slides as we go through this. So HCl here is known as hydrochloric acid. So it's obviously an acid, that the name gives it away. And notice that an acid donates H plus ions, right? And it's HCl. And so this H, which is marked as pink and red here, can be donated or lost. And then what's left over, right, is Cl minus, just a chloride ion in water. And the H plus has to go somewhere, and it's now bonded to one of the lone pairs on water, right? So now we have, this is H3O plus, because it has an extra hydrogen from water, and it has a plus charge, right? So here, look at what happens. HCl donates a proton to become Cl minus, so it's an acid. The water accepts the proton to become H3O plus, so it is a base. And I made a note here that when we encounter acids, they'll almost always have an H at the beginning of the molecular formula. So that really is like a nice hint that, like, hey, this is an acid. For example, HCl. And if you know the name of them, they all have the word acid in the name. So there's another nice giveaway. Okay, let's look at the product side here, right? So the neutral acid, HCl, loses a proton, and what's left over now is called its conjugate base, right? It basically, an acid that loses its hydrogen is now a base that could accept a hydrogen, and they're intimately linked, right? You can tell they're a pair, right? These two clearly go together. The difference is an H plus between them, right? So the acid becomes a conjugate base after it loses its proton. And now look at water. Water here is a base, but when it accepts that proton, it's now able, it could then lose that proton and swap it out. So it's now a conjugate acid. And we see clearly that these two are linked to each other within an H plus. So the water acts as a base, accepting a proton, and it forms a conjugate acid. So the conjugate acid has one more H plus and a positive charge compared to the neutral base. We'll come back to conjugate pairs later as well. So we'll revisit this idea. Let's look at another example. Here is ammonia, NH3. Okay, and this lone pair of electrons on the N is willing and able to accept a proton. Accepting a proton makes it a base, and so when it does do that, it turns into NH4 with a plus charge, which is now its conjugate acid. Oops. So you can see the clear connection between these two. NH3 is a base because it accepts a proton to become NH4 plus. And in this case, where did that proton come from? It actually came from water. So water could accept a proton in the last slide. In this case, it's donating a proton, and it becomes OH minus. So the water is an acid in this case. And this is, once again, pointing out conjugate pairs, which we kind of just did. So you can see, right, that these two are a conjugate pair, because the only difference is an H plus. All right, one last slide about water, and then we'll end part 1 here. So notice that water, in one case, accepted a proton, and in another case, it donated a proton. And so water is a special type of molecule. It can act as an acid or as a base. And these are called amphoteric compounds. Amphoteric compounds can act as an acid or as a base. Okay, we'll stop here and come back for part 2, and I have some more reactions, and we will identify the different acids and bases of these reactions. So come back for part 2.